Hi everyone, welcome to lesson 6 of the Advanced Higher Stats course. This lesson will be covering the binomial distribution and is one of many lessons that will be covering it. You will find this skill on page 21 of the 2023 course spec. By the end of this lesson, you should understand how combinations work. You understand the criteria X must meet to follow a binomial distribution. You should know how to display a binomial distribution, how to calculate binomial probabilities using a formula, how to calculate binomial probabilities using a data booklet, and that P and Q can be swapped. Let's start off with combinations. If given three different colored coins, red, blue, and green, how many unique sets of two coins can be made? We have red, blue, and green. And how many sets of two coins can be made? We can have a red coin and a blue coin. We can have a red coin and a green coin. And we can have a blue coin and a green coin. So 3, that's the number of sets that can be made, unique sets. Is there a simpler way to do this? Well, the way we did it was simple. But what if the numbers were greater? What if we were given 7 different colored coins and we had to find out how many unique sets of 5 coins can be made? Is there a way to do it more simply? And yes, there is. Would you look at that, the exact question I was talking about? If given 7 different colored coins, how many unique sets of 5 coins can be made? Now, I could write out every single combination, but that's a lot of effort. So what I can use instead is the calculator, and I can use a combinations function. So this is a calculator I have here, and how you get a combination function is by pressing Shift and a division sign. What you're trying to do, you're trying to click on the NCR button on your calculator. And now what's NCR? Well, C stands for combination. N is a number of different items you have originally. So number of coins in this example would be 7. We have 7 different coins. R is the size of the combinations we want. So since we want unique set of 5 coins, R is 5. What this means is if we put 7C5, we will get our answer, which is 21. One thing to note is there is a difference between combinations and CR and permutations and PR. For combinations, order does not matter. For permutations, it does. So if we look at the previous question where red-blue was a combination, we wouldn't call blue-red a different combination, but we would call it a different permutation. So red-blue and blue-red are two permutations, but red-blue and blue-red are the same combination. Late with binomial. Well, let's look at this question and I'll show you how it does. A football team is set to play 10 games. They have 60% chance of winning and a 40% chance of losing each game. What's the probability that the team wins exactly 8 games? Well, they have a 60% chance of winning, so if we can put that as 0.6 in decimal form. They have to win 8 times. So it's 0.6 times 0.6 times 0.6 and on, or we could just write 0.6 to the power of 8. So they win 8 times. And then you times it by 0.4 twice, you square it. So this means you are winning 8 of your games and losing 2. But this does not get you the probability of the team winning exactly 8 games, because this is only one of the many combinations that there are to winning 8 games. I want you to imagine a huge tree diagram for this. So for the first game, you have a win and a loss at 0.6, 0.4. And then you keep on going and going until you get to 10 games. Now, drawing a tree diagram would take too long, so that's why we would use combinations here. Now, one combination could be win, 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 loss, win, loss, win, win, win. And that's one combination. But you can move these wins around and you'll have different combinations. So how would you get that? So to get the number of combinations there are of winning 8 games, you would put 10 choose 8, because there are 10 games and you want to win 8 of them, and you want to see how many different combinations of those wins you can get. But even before all of that, we have to know when can we use binomial distributions. Because what I showed you there with combinations and probabilities, those are for binomial distributions. And there's one acronym you can use, and that is BINS. So B is for binary outcome, either a success or a fail. So you can either win the football game or you can lose the football game. There are no draws. You cannot draw. There are only two possible outcomes. If that's a criteria has been marked, we go for the next one. Independent trials. So let's say the difficulty of the opponents don't change. So if the team wins 2 games, that doesn't mean the chances of winning their third game decreases because they're playing a stronger team. No, if that isn't the case, then that's a tick. And number of trials is fixed. So this doesn't mean that the games go on forever and forever. There are only 10 games happening in this question, so this criteria is also checked. And the last one, the same probability of success in each trial. P is between 0 and 1. And this goes back to independent trials as well, and that succeeding 3 times does not mean your force succession is lowered or increased. They are independent. So we know this question fits all the criteria, and we know the problem-solving way of doing it by finding the combinations and also 0.6 to the power of 8 times 0.4 to the power of 2. Now, do we have to remember that? No. In our data booklet that will be given, we'll have this table here. It will have all the probability distributions, and we don't have to remember them off by heart, although it might be useful to do so. You will find this on page 4 of your data booklet, and you can refer back to this whenever you are feeling a bit lost at a question, and it can maybe help you. And what we need to look at here is this, the probability distribution function. With this, we can figure out what is the chance of a team winning exactly 8 games or exactly 7 games. We can't figure out the probability of a team winning more than 5 games without it becoming a bit tedious, and there are better ways to do that. So right now we'll stick with exact values. So if we say X is a win, we want 8 wins, so X equals 8. N is a number of trials, so N is equal to 10. P is the chance of success for X. So the chance of succeeding is 0.6. And that's all we need. Now we just need to write out the whole formula. So first we write probability of X equaling 8, or there being 8 wins, is equal to NCX. So we have N as 10, CX, which is 8, times PX. P is 0.6 to the power of 8, times 1 minus P, or you could even write Q, which Q is 1 minus P, and that's 0.4 over N minus X, or the remaining number of trials, which is 2. And if you do all of that, you should get 0.1209 or 12.09%. And that's the chance of this team winning exactly 8 games. Now, there's another way of doing this. Instead of saying X is the number of wins, we want it to be the number of losses. So let's not look at the team winning exactly 8 games. We can look at the team losing exactly 2 games. That would mean X is equal to 2. N would remain the same. N is still 10, the number of trials. P would change though. P is the chance of X happening. That's 0.4 for us. If P is 0.4, Q is 0.6. Now this is a similar way of writing it out. Probability of X equaling 2, because we want 2 losses, is equal to N choose X, which is 10 choose 2, times X to the power P to the power of X, which is 0.4 to the power of 2 times 0.6 to the power of 8. And here you would also get 0.1209. Along with finding probabilities, you have to be able to write up the parameters of each type of distribution. On page 4 of your data booklet, you'll find this table, and this makes it much easier. So what we want the parameter of the binomial distribution. So we have to find n and p. We know n is the number of trials, so in this question that's 10, and p is the chance of success, which is 0.6. So basically, you just replace the letters with numbers. So 10, comma 0.6. And that's basically it. Here is an illustration of the binomial distribution, where p is 0.6, same as our question. N is 20, so it's slightly different, but naturally 12 is the most likely outcome. That's why the probability of the outcome being 12 is highest. Then a 13 is the second highest, and then it's 11. Then 14 successes is the fourth highest, and it's 10 successes, and so on. It's more common to get more successes because p is greater than 0.5. Now, using the formula, try and do these following questions. A pharmacy job vacancy requires a 20 multiple choice question test to be completed. Each question has 4 options. If answered randomly, what's the expected value of correctly answered questions? This is simple. Expected value is equal to NP, which is 20 times 0.25, because there's 4 options and there's only one correct one, and that gives us 5. What's the probability of exactly 13 questions being answered correctly? Here, you use the formula 20 choose 13 times the number of successes with a 1 over 4 probability to the power of 13, because you want 13 of them to be answered correctly. And then the number of wrong answers to be 7. And that gives us 0.0002. It's actually 0.00015, but in stats we round it to 4 decimal places. Exactly 17 questions were answered incorrectly. So what's the probability for that? We can do 20. We can do either choose 17 and treat the incorrectly answered questions as the main focus, or we can just do choose 3 and still treat the correctly answered question as the main focus, but it doesn't really matter. 20 choose 3 and 20 choose 17 are the same thing. So I'll do 20 choose 3 for this. So we have 3 successes times 17 fails, and that will give us 0.1339. So far, we've been finding probabilities to exact values. So the probability of getting exactly 3 questions right, or the probability of getting exactly 8 wins. Now, what if we were asked to calculate the probability of getting 5 or less wins, or 5 or less correct answers? Now, we could write out and calculate the probability of getting exactly 5, then exactly 4, then exactly 3, 2, 1, and 0, and add them all together. But there is a faster way. That's by using the tables in our data booklet. From pages 7 to 9, we have binomial tables that save us from putting a bunch of numbers into our calculator, and saves us a lot of time as well. So how do we use this? Well, we look at the 3 values, n, p, and x. N is the number of trials, p is the probability of success, and x is the outcome that we want. So, for example, in a 12 MCQ test with 4 answers per question, the probability of x being less than or equal to 3 is 0.648. And how do we know that? Because n is 12, p is 0.25, and the outcome is 3. And we look at the table here. N is 12. You'll find that on page 8 of the data booklet. Then you go to the p-value, 0.25, and you go all the way down to x equals 3 here. And you'll get 0.648. The probability you'll get here is the chance of getting the outcome, which here is 3, or less than an outcome, 2, 1, or 0. So we know the probability of getting 3 or less correct answers in this question is 0.6488. But how do we find the opposite? How do we find the probability of getting more than 3 correct answers? Well, that's just simple. You do 1 minus the probability of getting 3 or less correct answers, which is 1 minus 0.6488, which gives us 0.3512. Using the method you've just learned, try and do the following questions. In a boring class, the pupils in the back row play a simple card game. One student picks a card from 5 cards. One is an ace, the rest are not. The goal is to get the most aces from 16 attempts. State an assumption which allows a binomial distribution to be applied here. What we're assuming is that each attempt is independent. So what this means is if the student grabs the ace and we're assuming he doesn't bend the ace or do anything that increases or decreases his chances of getting an ace the next round. Okay, so the next question is, let x be the number of successes. Find the probability of x being equal to or less than 3. First, let's write the parameters of this distribution. So n is 16 because there's 16 attempts. P, there are 5 cards and 1 is right, so it's 0.2. So we write the parameter binomial 16, 0.2. Now we use the table to get our answer. So the outcome we want is 3 or less. So we're already at the 16. We go to 0.2 and we go to 3. And that will give us 0.5981. Okay, so next question is, find the probability of x being greater than 8. So to get that, you do 1 minus the probability of x being equal to or less than 8, which is, and we use a table here, probability of it being 8, we go to 0.2, so it's 0.9985. So 1 minus 9985 will give us 0.0015. Now try these slightly trickier questions. So find the probability of x being less than 2. Now this is a bit tricky because when we find the probability in our tables, we find the probability of x being less than or equal to something. So here we have probability of x being less than 2. So how we would change that is very simple. Probability of x being less than 2 is the same as probability of x being equal to or less than 1, because this is a discrete probability distribution, so they're in integers. And for this, we just look at the table. Again, n is 16, p is 0.2. So that means 16, p is 0.2. So we go down as 0.1407. Okay, so the next question, find the probability of x equaling or being greater than 5. Again, when we do 1 minus probability of x being less than or equal to, let's say, k, what we get is the probability of x being greater than k. What this is asking is the probability of x being greater than or equal to 5. So we have to convert it first, and we change this into probability of x being greater than 4. And this makes it easy. So first now we need to find the probability of x being equal to or less than 4, which we can here. So 0.2, n is 16, so 4 is 0.7982. 0.7982. Now to get probability of x being greater than 4, it's 1 minus 0.7982, and that gives us 0.2018. Now try this final question. After each card draw, there is a 90% chance the teacher will not catch the students in the act. If 12 draws are attempted, are the students more likely than not to get caught? So here, the number of trials is 12, and P is 0.9. But the thing is, it's not, because if we treat it as 0.9, we can't use this table, and that makes things a bit complicated, and we want to use the table. So instead of treating the students getting away with it as a success, we have to unfortunately treat the teachers catching the student as a success. So that means probability, or P, is 0.1. That allows us to use the table, and now we can write the parameters, 12 and 0.1. Now let's find the probability of the students not being caught. The probability of x equaling 0. And we could use a formula, but we're using the table. So P is 0.1, and we already have n as 12 here. So for x to equal 0 or less, which it can't, it's 0.2824. And this is less than 0.5. So the students are more likely to get caught if they attempt 12 draws than not. That is the end of this slightly long lesson. Hopefully now you understand how combinations work. You understand the criteria X must meet to follow a binomial distribution. You understand how to display a binomial distribution. You understand how to calculate exact binomial probabilities using a formula. Understand how to calculate binomial probabilities using data booklets. And that P and Q can be swapped like what we did in the final question.